the last video, we introduced this reviews dataset that has various columns shown here. And what we plan to do with the data is use the information in the text column to try to predict whether or not a user would recommend the associated product. In that previous video, we handled various kinds of missing data, either filling in missing data or removing it altogether, in order to know that the data that we have is of high quality. Having made that assumption, let's focus on cleaning that text data to standardize for various things. An in-class activity that we completed was to come up with a very primitive natural language pipeline for the ways in which we wish to process that text data. That activity accumulated in defining this function clean sentence right here, which takes in a sentence as a single string and performs the following actions on it in a pipeline-like environment. First, we're going to split the sentence into individual tokens through a tokenization process. We then apply a stemming process to the tokens that were created in the previous step in order to reduce our vocabulary and combine words like lazy, laziness, and possibly lazed into a single token called a stem. We then created a self-made all punctuation function, which basically checked for just those stray punctuation marks that are masquerading as words, but aren't really words that are contributing to the sentiment of the text. And last but not least, we chose to remove stop words from our text in order to focus on the high frequency words that actually contribute meaning to the text in question. So that's a summary of the natural language pipeline that we decided on for this basic example last time. If we wish to see an example of the clean sentence function in action, we can apply it to one such text review in our reviews data. So let's begin with having our example sentence be the very first review in the text column. Let's print what that sentence looks like before cleaning. Then let's print what the function looks like after cleaning. So this first line is the actual content of the text column, and the second line is what it's reduced to after it passes through our pipeline. You can see that words like so have been removed because they are stop words, and words like has been stemmed to account for has, have, having, etc., and to just ha, and so on. So the basic premise of our pipeline is it's going to remove very readable text into a much more concise version of the text that still manages to capture the sentiment. This shows us an example of what that processing looks like on one sentence. We'd like to perform this action on all the different sentences in the text column of our reviews data. This will, however, take a while, so I've added a timing mechanism right here, and we're going to apply this process to every sentence in the reviews text. We'll do this for now with a list comprehension, creating an object called formatted text, which is the output of the clean sentence function for each sentence in the reviews text. So my cell has just finished running, and all of that took about 37 seconds, so a little while to wait, but not terribly long. One can imagine that the more steps we add to our pipeline, the longer this process can get. Now that that column exists, let's go ahead and add it to our data frame so that it's there if we wish to use it. So we'll add a column called formatted text to the reviews data frame, and we'll assign that list that we created of formatted text to the data frame via this line of code. And now we'll get into the statistics portion of what we need to take a look at. If we return to this recommend column, a user can either recommend a product or not recommend it. There are only two options. That's why we're calling the systems that we're working with binary classifiers. However, it is not necessarily equally likely that a reviewer would recommend a product or not recommend a product. And knowing this and getting a feel for what is that probability then is useful for us when we build models and we want to evaluate their performance. So what happens sometimes when you're building binary classifiers is people think that there are two options, option 1 and option 2. And if there are only two options, they must be equally likely. And so any model that does better than guessing at a 50% level should be considered a good model, right? Wrong. Let's see why. If we go to our reviews data frame and look at the recommend column and use the value counts method, this shows us that the vast majority of the recommendations are true recommendations. In other words, the user would recommend the product. And that's significantly more likely than the user would not recommend the product. And if we convert these raw counts to a probability, as we did before, by dividing by reviews.shape in that 0th spot to be accessing the number of rows in the data frame, we'll see that it's just about 96% likely that a user would recommend the product and only 4% likely that the user would not recommend the product. So if I want a model to be any good, I need the model to be better than 96% accurate. This is because I could make a very silly model that just believes that all reviews are good reviews. Every single time I see a review, I'm not even going to read it. I'm just going to say, yeah, it's a good review. This is informed guessing, but is guessing just the same, and it will be accurate 96% of the time. So our do-nothing, silly system of just picking the dominant class and making that choice every single time will be highly accurate, but it won't be very useful, particularly if those negative reviews are really the ones that you care about for making improvements to your product, say. This is one thing I would call a baseline statistic, or I would call it a class imbalance. And knowing what kind of class imbalance you have at the beginning of the process is really necessary information for changing your focus about how good subsequent models need to be. So in our next video, we're going to go ahead and we're going to build a very primitive model. And that early on question will be, is this model any better than the silly model I could have done? And when I say silly model, I mean the model that just predicts the dominant class every single time.